All right, recording going. So sorry for anybody watching online. We were talking for a sec about the project for this semester, which I was telling everybody here will likely be related to an optical tomography problem, most likely infrared optical tomography. I'll give more information a little bit later on because there's a lot of overlap between an X-ray tomography and an optical tomography problem for obvious reasons. In any case, that's kind of the we just spent a few minutes talking about, so you're up to speed. So for everybody who's here, and I guess anybody watching online too, I have put up for today another PowerPoint, just again because it takes too long to draw most of this stuff, unfortunately. So I'll download that. Cool. No slides will be shown. Awesome. All right, because they have. Okay. Hopefully the slides are being captured. We actually talked about some of this stuff last time. We're going to get into a little bit of the details, but I kind of want to put it together and to mention some of the topics we're going to be talking. So the plan for today, which is basically chapter 5, is going to be talking over the idea, particularly with a single X-ray image. And then the plan is chapter 6 goes into the CT version. We're going to mostly be talking on the how it's built direction and some of the key equations that relate to them. Most of these are not particularly difficult equations to get out. A lot of it is just being very careful when you're calculating stuff. So they give you this sample. They show you, a particular assembly here, patient, a table. I want you to realize this same exact setup. This one's kind of showing a vertical setup, where the camera is above you. A lot of times, though, you'll have the same exact thing, just rotated 90 degrees. Anybody ever had an X-ray done of them? You ever had one of like a chest or area like that? If you do a chest X-ray, more often than not, they have you stand for them. And so that, that table is now mounted against a wall and they can put the cartridge behind it. And you stand up to it. We'll talk about why we want to, and they'll have you press your shoulders and things in certain positions. Usually it's what they try to do is to capture accurately and move things based on gravity, right? Because soft tissue is going to move. So, if you want to get an accurate image of what's going on in the chest, the doctor usually wants to see it, relative to how you would kind of normally be standing, posture-wise, and things of that sort. So more often than not, they want you standing for that because then they can see kind of how your bones are acting when they're in those positions. But there are some times when you have to do flat. Sometimes that's due to an injury. There's a variety of different reasons. So you can see underneath there are kind of a couple things that are there. Number one, you can see there's an ionization chamber that's above them. For our purposes, we're not going to put an awful lot of emphasis on the ionization chamber. We're mainly going to be more concerned with the grid and the cassette that goes on. There's going to be a number of things you can do to both, filter things, to accentuate the image. Just think about the fact that when you get to that film, the film is very, very thin, right? Usually that film is on like a mylar or similar type of material. And so the actual exposable part, which will be some type of a metal oxide usually, that's going to be reactive in the range that, we're interested in, say some chromium dioxide or something of that sort. When you get that, it's really thin. So remember, our amount of dose depends on how thick your layer is. So a very important factor to us, and we'll kind of cover this more when we get it, is going to be how do we actually make sure we make that bright enough? Because otherwise, if you take a very thin layer on a very thin film, and that's all you're exposing to, you're going to have to put a really crazy high dose. So we've got to do something that's going to, you know, get them in the right range and then cause them to be bright enough onto the field. And that's what a lot of this assembly does. The grid is going to come in, we'll talk about that again in a little bit too. That's going to have very heavy effect on how do we prevent side, photons coming in from some weird angle, from, causing blur of your system. And we talked about that with like Compton scattering. Generally, you actually want the whole cassette assembly as close to the patient as possible. That's because there's going to be a magnification effect, which we'll talk about in a little bit. And the further out it is, right, inverse square law, it's going to look bigger. We can draw basic triangles. So the inverse square law will affect the intensity, and then, the basic triangles we're going to draw is going to affect the size and the magnification. So generally you want that pressed. So there's usually a table to create structure or, a shoulder mount area, and the cassette is as close behind it delta some of these other protection areas to get a good image. We'll talk first about what's on top, right? X-ray tube and housing, and then a little bit into the collimator, collimator, so that we can, the idea being that we want it kind of directed in a particular way, and we want to get everything moving as nice and straight as we can. And then of course we'll talk about the patient and effects. Things in the front of your body are going to look bigger on the film than the stuff towards the back of your body. There is a relative scaling throughout your body, and we'll talk about why when we get to the magnifications towards the end. So this is, if you understand the picture on the left, it'll kind of follow what we're going to talk about. We're going to do the top, and then we'll do kind of the bottom stuff, and then we'll get towards the patient in the middle. So let's talk a little bit about how we actually make this X-ray source. Did anybody have a chance to read the chapter already? Yes? Fine. Do try to. The book's actually pretty good. These pictures are from there, and I was trying to tie them into your reading area. They did a nice job of taking the picture, and that is the appropriate picture for it. What you'll see on these, right? The basic idea is there's two basic controls. We'll see on the next slide. But if you look right here, I've got basically a cathode assembly. That's this top part. And I've got the anode assembly. And then I have this lovely glass tube. Why have the glass around it? It does filter. That is absolutely true. So that is one of the reasons you care about it, right? So you'll select the type of glass to effectively filter it, sometimes putting a particular window in an area that you're concerned with if the material that you want to filter with is not necessarily as cheap or as durable as some of the other ones. So you'll sometimes create a special window in there. But besides just the filtering, right, I could just put a filter on one side. Right? Why do you think we might need glass all the way around it?
Could it help with heat dissipation?
That's a very good question, right? Can it help with heat dissipation and other things? So heat is a huge issue to us. Right? This is actually going to prevent airflow, right, which will be important for something. Right? Most of your heat's going to come here, come down this shaft, come down here, and we usually have a cooling block on the kind of this lower left-hand corner of it, where you see the metal coming out. Will often cool that because heat is huge, right? But our glass is not going to give us a huge help towards heat removal. When you hear anode and cathode, what do you normally think of? You see some weird metal device with a gap, and you hear anode and cathode. Do they talk about kind of early physics technology, maybe in your second physics course? It's usually where Like your first physics course was like Newtonian stuff, right? Your second was E&M. Okay. When they did E&M, did they talk to you about some of the early technologies they used to do these tests? Or did they just go through the equations? This is just a curiosity on my part, because I'm not going to successfully be able to tie it into something if they didn't say it. So,
I think they mentioned the experiments, but I don't remember.
all right. So part of the reason, so I would encourage you, like when you hear stuff like that, it always sounds like it's just like some, irrelevant piece of junk, right? But it's actually really useful to you as an engineer. Because the question is, how do you make that? So the early experiments will tell you at least the most direct way to build something, right? So let's talk about why this goes in here, because I want you to understand how something is designed. In particular this, because partially you're an engineer. I mean, who knows what you're going to do in the future? You might end up having to build it, or at the very least, knowing how it works is going to be very important to help people understand. So the glass is there because it's actually to keep air out. So much like a light bulbs have glass around them, depending on the light bulb type. If it's a standard light bulb, it's to keep air out. That's the same thing for this. If it's a fluorescent tube, it's to keep the particular neon gas that's in there from mixing with everything else, because you need the neon to be able to generate the light, right? So they keep a concentrated, neon gas in there, impose an electric field off it, and current starts to flow. The current flowing through that causes it to emit characteristic light, woohoo, neon light bulb, right? So in our case, we're more like a standard bulb in this sense. We don't want air there. Does anybody know why we don't want air for a standard light bulb?
Something like blow.
Yeah. You ever see the last second of a light bulb, right, that you can use? What tells you your light bulb, besides the fact it's not on anymore? What usually is easy to see a company just before the light bulb is useless? A flash. Why? Yes, exactly, because air got in. That filament is so stupid hot, if air gets in, right, it'll actually now you've got heat and oxygen, so now you can have that lovely chemical reaction. So it does exactly that. You get that kind of, and then it's all over with. Right? It turns your lovely filament into a burnt filament. Our concern is not that it's going to burn up. Our concern is more related to the physics experiments that first went on when they were looking at some of these. I'm going to produce electrons right here where it's kind of pointing to the cathode. See that little thing sticking out to the side? That's actually where the cathode is going to be affected on, right? That's going to be the source of our electrons. We could put it anywhere. We put it here because we want to hit the side, right? Because we don't want to have to travel through material, right? So we kind of hit the edge so that everything's going to come straight off on the other side. This is going to produce electrons. We're going to make a move really fast and slam into this. What we don't want is something in the way of our electrons. So imagine I'm making an electron gun effectively here. Air actually will disrupt the path of your electrons falling. So you've got to evacuate it. Otherwise something blocks your electrons and they scatter out all over the place. They'll still make it down here because they're attracted to this, but it will no longer be a nice tight spot. Right? So it'll have all kinds of problems. And then the air will heat up and all kinds of problems can happen. Right? So we have to get rid of that air so we get a good clean functioning to it. The actual behavior, even though this looks really sophisticated, is stupidly simple. Right? We'll talk about more in detail. But on the next thing, how that part works. I just want to get over the components. So this is off to the side so it can hit the edge of this. Yeah.
So I'm assuming, because you have a label with a stator, is the disc like a rotor and it rotates? How
It
fast
does.
does it go?
Right? So the speed that it's going to rotate at will depend a little bit actually on how many electrons you're releasing.
Mm-hmm.
Right? So the question is, why do I rotate it at all? Now, the rotation has nothing to do with the production of the X-rays. right? The electrons strike it, they produce the X-rays. That would be true even if it was not moving. Now think about it. Electrons are ramming into this at really high velocity, right? A reasonable fraction of the speed of light. So there's a lot of energy in these things. As a result, what's going to happen to this? It's going to heat, right? If you have it constantly in one spot, it'll heat up too much and you got a problem. So we make this really big disk so it can spread around. And then you just set the speed of rotation depending on how much you're sending down so it can rotate and allow you to spread the generation of heat to different areas. So it's, we're not going to do it super fast. It's just going to spin purely so that we could spread the heat on it. If you didn't, that area would get too hot and you could actually melt it and do other problems. It's no longer a good source. So we're going to run this high enough that we're just going to want to spin it so that it spreads the heat out. And that's really the whole reason for it. That's why it's big too. It looks fairly decently chunky and comes down. You can see the stators kind of come on the outside of this and are going to rotate it. There's a central shaft with bearings. And so the whole idea is to be able to bring this in as much as possible. There's all kinds of fun stuff you can do with these, with cooling and, very often we'll use copper, material and through the center because it conducts heat really well. So there are some pretty neat ways to be able to do these, but that's the basic idea of it, this whole point. And you are correct about the stators. Rotate purely for heat dissipation. All right, we feel good, basic idea? Okay, there's two parameters we care about, so I kind of set the next slide up to be able to demonstrate those. Okay, everybody remember this lovely chart? I put the straight line in. It should have those spikes, and I was going to add the spikes, but then it was overlaying the other ones and you couldn't see them. So I just kind of put the blue line is the production source and would also have those same spikes, the characteristic electron ones. But just to give you a reference where it's coming. Right? Leaving the tube is when it comes out the window. Very often we do a beryllium window. Right? Does a good job kind of killing this very low energy. We call that hardening the beam because it comes up. The softer ones go away, the higher voltage, harder ones stick around, so the net effect is it quote-unquote hardens. Very often we'll put a filter after this. This is still in the main assembly, and so this is leaving the filter. And we'll assume that these X-rays are going to have enough energy. They're probably not going to dissipate in the air between that source assembly and you. So leaving the filter is also probably pretty darn similar to entering the body. And then this is leaving the body, and the difference between these two tells you how much you lost, and that's the image you're trying to get at. Right? So that's where this is. This is a statement of the number of photons per energy. So if you remember, that was our S of E, right? Based on E and S. This one is relative because you take the relative intensity, that's characteristic of your design, and you multiply it by the filament current. So this has been just normalized scale-wise. If you turn up the filament current, you just increase the intensity. So it just becomes a straight scaling factor. So that's why it's a good idea just to send the normalized. It's based off, a unit value range that's on here. How much would you get at? And then they'll set whatever it is. Usually, these are in fairly low on this because you don't need an awful lot. This tungsten filament that's in here, that's this part, that was that side assembly sticking off. The current that runs through here, just like on a regular bulb. On a regular bulb, it produces light and it generates heat. It gets crazy hot. Right? In our case, it is not going to produce light, at least not in any range you can see. Right? we're really going to keep it fairly low, so this would just be down in the infrared anyway of anything that's being produced. It's not going to produce anything in an interesting range to us. But what's going to happen, everybody's seen the basic electron shell levels, right? Think about a metal for a second. Its very top electron, right, and that valence area, how close is it to the conduction? Yeah, it's really close. The other thing is, if you take that distance between the valence electrons shell and the next shell up where it can start moving about, there's an energy level that kind of sits between these. Right? This is called the Fermi energy. Right? So if the Fermi energy is really close to the conduction band, it's way up here, that's a really good conductor. Because what that's saying is, this is the amount of energy due to temperature. Right? It's enough to lift that electron part way, but you can't actually lift it part way. So what effectively happens is it becomes a probabilistic amount, right? So if it's part way up, right, like if it was dead in the middle, you figure it's 50-50 chance that it's going to promote them, right? So, you know, it's not exactly, but it's simple enough, at least for the image, right? So if the temperature is higher in the average spot, so this is kind of your room temperature, where is it? You got a fairly high likelihood that electron comes out. If the electron comes out, that means those electrons jump out and they're kind of hovering in and around the filament. If I took the temperature and I raised it, guess what happens? I raise it above that level, I'm going to start promoting electrons like crazy. Right? So we call these thermionic electrons. Right? Just think thermal. And they're thermally produced electrons. And this is a byproduct of something just being a good conductor, and metals are good conductors. That's why we use a metal filament there, tungsten. Because it's far enough out that to go, the difference between that conduction band and infinity is really small. So as we raise that temperature, it's going to promote it. Well, therefore, the hotter this is, the more electrons I get. Right? It's actually pretty linear in this region, so that's pretty nice. Temperature proportional to electrons. Well, temperature is also proportional to how much current you're running through this. More current, more temperature, more electrons sitting around to accelerate. Therefore, the available electrons to produce X-rays is proportional to the current in the filament. So there's two things we really control, basically, when we do an X-ray image of something. We can want to control the intensity of our source. That's controlled by the filament current. And so hopefully that now makes sense. All this does is just generate the electrons. So just think of it, a little coiled wire, tungsten, thermal heating, right? V equals IR stuff, that produces your electrons away you go. Right? Pretty linear in this stuff. Then what we're going to do is we're going to put a cup around it. Now the reason why we put a cup is it's to focus things. So imagine I just had the wire there all by itself. We're going to impose a voltage which will start accelerating in that direction. But if I'm aiming at a really big target and it's all the same voltage range, it could pretty much go anywhere. Right? So you can imagine, I don't just want it to go anywhere on the opposing side. I want it to hit the angled part of my edge. Here we just show it with, I just found a simple picture on the internet that just showed, you know, a metal target on angle. You can imagine it was the disc and stuck out. This one just had it easier to draw things to annotate. So if it was just general, those electrons could spread out across that whole thing and I no longer have a precise spot. Okay? I want it all coming in one direction, which means I want a really focused spot. I want to know the electrons, not just they're going to hit the anode, but I want to know they're going to go to the anode in this particular location. Well, the anode is going to attract it everywhere. So how do I force them to go in the direction I want? Well, the best thing I can do is if I put a cup around it, they can't go off to the side because then they'll be getting closer to an equally negative charge source. They don't want that. They want to go out as far away from the cup on either side. So if you imagine the filament in the middle, they're going to want to come out pretty straight. Once they're going straight, the field will keep pulling them straight. They're not gonna diverge as much. So we put that cup in so that the negative voltage that we're putting on that side, what makes it the cathode, right, is gonna be able to also channel the beam. So in addition to accelerating it, by changing the shape of it, we also are able to cause the beam to go in a particular direction we care about. Does that make sense? So it doesn't show it here, but if you look on the previous picture, there was that kind of like indent area that the filament was in. That is that cup that channels them. Okay, but the main thing, this is the cathode, that's the anode, so there's a voltage difference across here, right? That's that kVp, the P just means peak, as what that maximum is. Since both sides are equally charged, they go across the same voltage field no matter where you hit on that. So it doesn't matter where you strike, you still went through the entire field strength. So let's say, for instance, like on this chart, you could see, right, kVp is, 1 electron traveled across that voltage. So that's what the EV is. And you can see here it's 100. So that's 100 kilovolts was imposed across here for that chart. You'll get lower value stuff because remember, there's all kinds, right? It can, things can come off at different energies, right? Caused by, depending on where did it hit, and you can get the characteristics as they drop back in. So the lesser stuff can always happen, right? But the maximum energy one can only happen, right? The perfect collision. It happens if I hit dead center, aiming at the atom. The further out I hit from the atom, the lower the energy gets. Until eventually I miss, which is 0. Okay, we feel good about that? So that's the two things. We control this to set what you want to image. The stronger it is, the better penetration it's going to have. So that's going to set essentially how deep of an object can I go through, right? If you set it really deep for a really small object, there'll be no effective image that comes out of it. You want that depth to be enough to go through, but to have lost a lot, because that'll be the contrast range you can pull out. Right? So too big on this one, it's going to expect a really thick source. If whatever you're trying to image isn't, no good. Okay? And this, the current in the filament will determine what is the intensity. So you can kind of think this range here is controlled by the voltage between the cathode and the anode, and the absolute intensity of this graph is controlled by the current flowing through it. So, and that's S0. So if you look through, right, the S, the source intensity of E, throughout the chapter, it's all over the place. So these graphs are what they're referring you back to whenever they use those. The book will include a lot of integrals because it's true, those are there. However, you pretty much never calculate those in real life. Right? It's just, in general, you look stuff up on graphs. You tend to actually calculate these in a computer, right? So you discretize it and then have code that's written to sum it up. In general, you're actually given usually code that's been checked very heavily and that a particular place is purchased. You might be the person who ends up writing that code, right? But whoever it is, there's usually existing code, you modify stuff, you check it like crazy against everything because a lot of people are going to be affected by its accuracy. So in general, in real life, most people don't tend to calculate those. They tend to use existing software to do those. That being said, even if you don't write the software, you still have to understand how it works, but you have no idea how to adjust those numbers. You get a magic answer out, and somebody says, I need more of whatever, and then you have no idea what to do. So this trade-off is actually one of the most important skills. Everybody needs to get that. To get the exact formulas, which we actually covered last time, right? Remember the integrals we calculated, or the integrals we showed in there? Like I said, you don't really calculate them regularly, that's why I'm not sweating them. I just want you to remember they're there, right? The S0 of E times E essentially integrate that from 0 up through the max energy range, will give you effectively what the source intensity is. All right. We feel good with this? All right, so at this point, we've got a pretty good characteristic of what is the source that's going to come from here. The difference just being this filter. All right, between what's produced at the tube and what's not. Okay, so let's talk a little bit about filters. 2 different types here, one of which is collimators, if I can never say the word right. Those are kind of shown on the top. Okay? What we often have to do is restrict the beam to some basic geometries. So imagine I was just doing a chest x-ray, right? And let's say particularly that the doctor was just interested in an image of the heart. I do not want to give you radiation. You know, your heart's kind of sitting under the sternum and a little bit to the left. Right? Is there any benefit to getting radiation on the right side of my chest? How about through my abdomen? What does the doctor want to see? The heart. So what I should do is I should restrict the field that my source is going to be to the area you want to image. Don't image more than you need to because you're just radiating those areas. And yeah, you'll get an image, but the doctor doesn't care about that. So why give somebody dose that doesn't benefit them? So you can see on the right an example of that kind of one. You can see a basic diaphragm one on the left, right? The basic diaphragm restrictor, just kind of think like those old camera lenses, and you can spread them out, right? A lot of ones have these collimators that are kind of XY ones. They've got an aperture. You can kind of think of like margins on a page, right? You can set the left, right, top, and bottom. They're restricted very often because your films are going to be that size, and you know, you'll see when they line you up, they'll actually have a light source that they're going to have a mirror that they can switch inside, and they'll rotate so that actual visible light will go through the collimator, right? Collimator, right? And it'll go through it, and it'll show the light right on you, and the person can just adjust it, right? They'll usually adjust it also, you know, take a look at it on the actual cartridge area too to make sure their cartridge is set in the right spot and things of that sort. All right, so between those, they can accurately do that. A lot of times we care about cone beam restriction also, which is a particular geometry. We want it centered around the beam, right? And we want an actual cone. There's also what's called a fan beam, so it's very thin. It's kind of like a fan wedge, so you think like an arc. It's in, those geometries will become very important when we do CT scanning. So you'll often hear about CBCT, cone beam CT. It's telling you the source was a cone beam, right? There'll also be CTs that use a fan beam, right, to do the imaging that they're then gonna overlay to make the CT scan. So that's just showing you how do you restrict it. What you're trying to do is you want to let it through completely in the area you're trying to image, and it's usually a thick enough metal piece that it should hopefully stop it completely on the outside. All right? The filters on the bottom half, beast of a different kind. Your goal on the filters on the bottom half is to adjust for it. Probably the easiest one to think about is the foot. Right? If you look at your foot, as you go towards the toes, it's getting thinner. Right? So you imagine, you know, the bones are not hugely different thickness-wise all the way through your foot. There is a little bit of a difference. There's also a little more bones kind of in your heel / ankle area. So generally, if you're looking, and I want to get an even exposure all the way through. And again, remember, even exposure isn't just so that it looks pretty and even for the doctor. Remember, the range of energies coming in versus those coming out tell you your ability to get contrast. So if you've got too much coming in the toe region, it's going to be like a washed out image. It's not just that it's going to be the different intensity. The range of them is not very well, so it's going to saturate. You're not going to be able to get a good distinction of them. So it's more than just try to make it all look nice and even, though that is an important goal too. We also needed to have a good entry range so that the contrast, which is proportional to that entering energy versus the outside, is going to give you a good possible range of what's there. So you can imagine, like, you know, I could put a wedge, which is like a foot backwards. Okay? And so placing that, right, inside as a filter, so you get your X-ray radiation coming out, it's been collimated, I can go through a wedge filter. Sometimes they'll you know, have another collimator, just a collimator to prevent any spreading that's going on. And I can use that, and now I've got the proper range of frequencies going through, so I can get a very good contrast, right, and see all the structures. If you imagine this is kind of like a cross section, here's your arm, pectoral muscles, there's your back and your spine. You're thickest here, you're thinnest on the outside. So therefore the filter we want is a trough, right? The exact inverse of that. So again, we get an even amount of energy coming through. There's a similar one, that trough we do for the head. Remembering also that we often will have some type of a cushion that's going to try to keep the person's head still. You don't have as much of a problem with this with the chest, although you might. But usually people aren't moving as much on their chest, but your head, we move tiny amounts without even thinking it on our heads. Any amount of motion causes motion blur, and this just gets ugly really fast. Particularly when you're trying to image very small bones or other structures inside the head. It's just no good. So there's always some type of a filter around there. So in essence, we usually try to have that trough plus the kind of pillow holding it together, you consider as the overall shape of what's going through. We feel good with filtering.
I have a question about the collimator
Sure.
image. So the book mentions that there's oftentimes different layers, like it's shown there, there's 2 layers.
Yeah.
Are the additional layers useful for anything other than just additional, like, canceling of the external rays? Or
Very often you put the filter in between them.
I see. Okay.
Right. The filter is usually a material that's not going to break down as bad, and it's scheduled to be replaced regularly. Generally, you don't want radiation hitting a metal structure unless you're going to be replacing it on a fairly regular basis, right? Because high amounts of radiation hitting metal over time makes that metal become slightly radioactive. Right, so we generally don't like that. Right, so most of the things are designed when we have to have these type of things that you can have them regularly tested and replaced as part of the maintenance structure. You know, if the filter is generally pretty cheap, right, and you're going to replace it anyway, so if I kind of put it so that the attachment points are kind of outside of it, it reduces and simplifies my replacement scheme for maintenance on it. And you figure something's going to get scattered inside, right? I also don't want some of that stuff scattering and coming back at my interior area, right? So I've deliberately tried to send it this way, right? If it hits a material and I get some back scattered stuff, right, due to content scattering or things of that sort, don't want the radiation coming back either. Good questions. All right. So this shows you the other half of this, the attenuation coefficients. So we've seen attenuation coefficients before. We talked about these, probably right? I'm really just doing this, number one, as a reminder, but also to let you see some basic functions. So we had talked about this before. This is overall attenuation. We talked about several different sources and effects on them. Remember the Bremsstrahlung, the breaking? That's what's being used for electrons converted to X-rays. So that's all at the source. All the other ones, the Compton scattering, your pair production, your Rayleigh scatter, all the rest of this fun stuff, right? The characteristics, all these kinds of fun stuff. All that has to do with these attenuations, right? So for our purpose, the attenuations are going to tell us kind of based on how far you go, right? So the attenuation, most of these are going to be mass attenuation, right? If it's a mass attenuation, this one is not actually, right? If it's a mass attenuation, you have to multiply the attenuation factor times the density times the distance it travels, right? And then that's going to be the factor that goes into e to the minus that. Right? If it's just a linear attenuation coefficient, then it's just that mu times the distance x that it travels through the path length, right? And that's going to be e to the minus, right, mu x. So this is basically telling you how much it's going to interact, right? As the linear attenuation goes down, it's interacting less, i.e. higher energy stuff, you can see the attenuation coefficients are smaller, therefore it does not slow things down as much when it's high energy. That's why we really can kill off the low energy stuff, because remember it was useless. If we don't filter it out, it's just going to end up inside the person, dose with no benefit. Okay, so this one shows you a couple key things, right? You can see here, fat is the lowest line. Muscle, kind of soft tissue range is the next line up. And bone is the next curve coming down, right? It starts out a little bit below, and it comes down. Actually, I think it starts a little bit above, right? The important thing about these, right? The difference in these attenuation coefficients will tell you your ability to image. If your entire object, even if it has different structures, if the attenuation coefficients are really similar, there's going to be almost no difference in absorption of photons, which means there's no difference in the image. So you need things to show a strong difference, right? So you can imagine these three. This kind of gives you, fat is on the lower end. It's not the lowest. Your lowest is like, honestly, the alveoli and stuff inside your lungs. Some of the mucous membrane in your nose is actually even lower than this. They're almost down to the air range, so they're really down here. But for most practical soft tissues, you can see are in these lower two band lines. And then bone is like a significant jump from them. So imagine these two bottom lines are in some sense giving you a range of soft tissue imaging. And then the bone line going up here is giving you what you classically see with bones. That's why bones show up so strongly on x-rays, because that attenuation coefficient is a huge difference. But imagine they were down in this range, and that's what you're trying to see the difference. Right? And we often use x-rays for something that honestly x-rays are not good at, which is determining and finding tumors. You ever hear somebody gets cancer and they're like, okay, well, let's take a CAT scan. Right? Well, CAT scans are x-rays, and x-rays do a bad job of differentiating tissue. So why the heck would you ever want to do that?
It's cheap.
It is cheap. It is a very economic way to do this. That is definitely one of the advantages. Right? There's a couple other ones too, though, that are in that same ballpark. So 100%, that's a big one. Right? We've got to make healthcare affordable.
Is there a different attenuation for like cancer cells?
It is slightly different, but not different enough. All right, so we're going to have to do something about that. But that's not the big one that we go for. It's still the difference between it is still going to be in this little narrow range down here at the bottom. How often do you see a CAT scan machine in a hospital or a clinic or something like that?
Probably.
They're all over the place. I guarantee you go to even one of these little emergency rooms off campus, I guarantee you they probably have a CAT scan machine. Right? MRIs, rare. Really big MRIs, super rare. So for availability, CAT scans. That huger availability means cost differential is better for your advantage too, making it even cheaper of a cheap source. Right? There's one other reason. it's gonna be really good in spatially determining the location. So the doctor has to be able to determine how big is that tumor, right? Well, a CAT scan is gonna give him or her a very, very accurate measure of the size, right? So that's another big reason why we care about this very much. So now I've got something that doesn't really do a good job of what I want, but there's a whole host of reasons why I want to use it, right? It's guaranteed to be there, it's economic, so it keeps things affordable for people, right? It's got good spatial locality, so I'll be able to find things and scope the edge of the tumor well to do treatment planning, a lot of things I like. Problem is, it stinks at actually making the image. So what can I do? What I have to do is change the attenuation of tissue. How do I change attenuations? I gotta add a contrast agent. Yeah, just like you would add dye to, I could add like blue food coloring to water to change its attenuation of visible light. I'm gonna pick another substance your body will absorb, and different tissues will uptake in a different ratio. That's gonna be able to handle, create a good contrast between them. So I need something that's probably at least bone range, right? It also has to be something, since you're gonna be uptaking this throughout your whole body, it should not be poisonous, right? That doesn't mean it won't be disgusting. Right? Sorry, but all of these are totally gross. I've never had to take one, but I've known a lot of friends who have had to take them. And the universal response is, it is the worst thing they have ever had to take. Usually you have to drink these, and it gets absorbed, and then you have to wait for it to make it into the tissue, and they have to image it in the time window between your system uptook it and it diffused through, but before your body removes it. So they gotta kind of calculate your metabolism and figure out how that's going. Here are probably the two most popular families of them, are the ones you see with these kind of edges here. So we use them based off of either barium or iodine, right? Now you don't want either of these in huge doses, but in small doses, they're totally fine, right? You have iodine actually added to most salts, right? For a couple different reasons, but one of which is actually radiation. So if you've ever heard of people iodized salt, that originally started getting added in during the Cold War as a protection against nuclear war. It turns out it's also fairly effective on things like sunburns, so the ultraviolet light and other things will not make it as bad a situation for you. The iodine interacts with the higher energy ones, it gets the effect of it, and you waste removal. So it is a helper overall to your body. Right? So it's one of those Cold War things that ended up being a little bit beneficial. Not all areas of the country do it, because some areas you naturally get it. So they try to actually place, depending on where the salt is, you'll find some areas don't have iodized salt and some do, right? And that's usually dependent, do you get it or an equivalent from a natural source? You can't get too much of it, too much bad, right? So that's another reason why you don't want to overdo it on the salt, but you actually really should buy your salt in the region that you're using it, because you don't get just straight salt, you get modified salt. And so they try to adjust it for the region that you're in. This is not a good one to buy, on Amazon or something where they're not region specifying it. Little weird side thought, right? So barium, right? So you can see we have a particular one, right? Barium sulfate, right? There's one of them. You notice it's right around bone or a little bit higher, going to create a good contrast. Barium is viscous, right? It's like drinking syrup. That also means your uptake will be a little bit slower, but it's a good contrast. You get rid of it fairly quickly, things of that sort. I've been told totally disgusting. The high pack up there is an iodine based. Right, so I just put that because that's a particular trademark name. But just so you know where it is. Like the book will mention you use both, but then they don't tell you where the other one is. So that other one is, right, that's iodine. You can see it's a little bit higher. Right? It'll give a really big contrast to it. It is a more liquidy substance, so you get the associated benefits of kind of quicker dissolving and everything else. But there's all kinds of other disadvantages with quick too. So, yeah. But anyway, those are the two dominantly used ones that are there. Remember, you really only want to use them also above that K edge. So if you were doing a mammogram, I'd pretty much be stuck with a high pack, because I want to be somewhere in that 30 zone. So I'd rather have that the low end of the 30 zone. Remember, too high of an energy, it's just going to blow right through soft tissue. So if I was trying to distinguish between a soft tissue tumor in a breast versus a regular tissue, you're going to have to stay in that low energy range so you get good contrast. But you need a contrast agent to accelerate. If I go up to 37.4, I need to go safely above that with my peak energy. All right. And now I'm going to have a bunch of radiation that's just going to wash out the film, and it's going to reduce the effectiveness. Don't like that. So, if you've got small things, so that's true. Like if you were looking a similar area, if there was cancer in your foot or hand or arm, something thin like that, as opposed to going through your entire chest or head. Very often when you're dealing with the biggest area for most people around, which is going to be, your whole gut area, you're pretty much usually in the barium zone. Again, you don't want to go past the barium zone when you're dealing with the intestines area, like looking for, like let's say cancer in the colon or things of that sort. You don't really want to go beyond that, because again, if you get too high, now you need to put so much to get through it. Right? Just creates more of a problem. So if I had gone to the iodine-based one, it's going to be too strong. Right? So I won't get a good image in that sense, and I'll have to increase my rads. Okay, we feel good with this. Just kind of a discussion. These are again just some overall thought areas on them. If I were using that, I would know. I could look at this, the attenuation factor. So remember, you would take, we know the S of our source, so I could say, at 100, I take maybe, 5 kVe or keV on, on either side, and look up, I could get what the attenuation coefficient is for each one. I could break it into little pieces, and I can multiply them times their source and the distance traveled, put it in the equation, and away I go. Right? So, these curves are used with the previous ones to basically generate the stuff. Okay, really quick on here. This gets into how we do the spacing. So this is for our grids. You can imagine with any of these grids, I can basically, I don't want to make an actual grid. Usually what you do is you've got these long row ones, and I can do it in two directions if I want it stacked. Typically these are made from lead. So imagine how on earth am I going to make a good, nice, strong lead in like lots of little squares. So it's generally easier to have them in length. In theory, you could do on other, you could make a grid one to them. Generally, I've seen them done this way. I'm not going to. X-rays are not my biggest area, but at least the ones I have seen have been more this style. So what we really care about on this is the ratio of the height to the width here is going to determine an angle coming in. So if you imagine the X-rays coming in, something coming at an angle more than just height over width, that ratio, you get the angle. Right? Fairly straightforward, right? That's just, tangent is b over your h, right? That'll tell you what your angle from the normal is. It'll cut out anything from that. Typically speaking, height is much higher than width. So we always do it usually a ratio, an integer ratio of h over b, and it's typically something like 8 or 16 or something in that range. So it's really high compared to the associated width that can go through. So you get a very, very narrow angle range. which is the goal, right? We're trying to stop that content scattering. That prevents blurring the image. That's the whole reason you do this. The grid is there to prevent blurring. That ratio just tells you what angle theta is going to be permissible. Anything else gets removed. And this is really all due to the content scattering. Good? To me, it's a pretty straightforward idea. Very often there is something, interstitial space, right? There's often a material in there to keep you from bending these things. So something that has like a ridiculously low coefficient, but it provides some structure to keep them, because otherwise lead is ridiculously soft and easy to bend. All right, let's talk about what happens inside. So there's still a lot of film cartridges out there. In general, we hate film cartridges. Ever know why we hate film cartridges? They're what?
Animal.
Yeah, it encourages Charlie in this delusion that analog versus digital stands a chance. No, that's it's actually because, remember what I was saying before, how thin it is? The response is very small. So we're going to have to do things to accelerate. What that usually means, since that response is really tiny to it, we have to up the dose to expose the film. Right? So this is why if you ever hear, like your dentist, like a lot of dentists have been switching from film ones they stick in your mouth to those little detectors, right, which has the wire, right? The detector with the wire is way more uncomfortable in your mouth, right? It's a slightly bigger thing, and then you got the stupid wire coming out and everything else. So why on earth do it? Well, because it's easier for us to get a response in the silicon, right, to it. We can do a better job with less radiation. So it reduces the radiation exposure to the person. You can do a smaller amount from the source. You just can turn down that filament current, and you get the same quality. So that's why we care about it. And the real reason is we don't have good materials otherwise, that can compare with what we can do inside the sensor. If we could do better inside the film than the sensor, then I'd be all for it. There are a few places where you just don't have space for the wire and everything else, so you have no choice. You have to use the film. So there are places that generally you can't avoid it. But in general, if I can avoid it, I would suggest avoiding it just to reduce the dose to your patient. So how do we actually do this? Well, some of the challenges, let me actually start here at the bottom left-hand corner, right? Because it'll help to explain the other stuff. I probably should have stuck that one up there. I was just throwing them in. All right, the base, just structure. You pick it so it doesn't move those things very much. This reflective layer, what we're going to do is we're going to put a layer of phosphor. This is the one to understand really well. And we have a protective coating just to keep things from getting scratched and problematic. What happens with phosphor when it gets hit by radiation? Glows, yeah. Anybody see an old TV set, like 40, 50 years ago? Right? They were really huge tubes, and they're, actually even up through the 80s and early 90s, they had a lot of these ones. They had an electron gun, and you fired it at it, and it caused the phosphor to glow. Right? Essentially, it takes higher energy stuff, and you're seeing a characteristic radiation after it got energized. Well, its characteristic bands are in the visual, but that means it's lower energy. So if you get a really high source hitting it, and it's going to dump off a small thing to dissipate it, what's going to happen? One big one, I have to dissipate it with little ones, so what am I going to get? A whole bunch of little ones. It multiplies it. So it's a material that effectively increases the gain on your photons. They're going to be lower energy photons, but who cares? Right? As long as it exposes the film, and chromium dioxide works perfectly fine in invisible range. So we have no problem with that. And if I can get dozens to one or so, why not, right? That drastically improves things. But when it does that, characteristic, it's going to go in all directions, right? So some would go back in towards here. So we put a reflective layer so it comes down. We do this on both sides. The film's here, this is here, it's on the other side. So the film is sandwiched between them. These things are part of the cartridge, the person sticks the film into the cartridge. This, you can see the material, this is just the structure to keep it rigid, right? Inside this on both sides, it's got this on both sides, that's just structure, right? It's got a thin reflective layer, usually titanium dioxide or something of that sort that'll reflect fairly nice. Then the phosphor layer, then a protective film, slide your film in, boom, slap it shut. You'll get exposure from both directions from the phosphor. Now think about the top picture. This is what's happening. X-ray comes in, right? You can see this one is just showing the phosphor layers on either side of the film. It's not showing the protective coating because effectively, if you do it right, the protective coating shouldn't really count very much. So we're just ignoring it for the moment, right? It hits something and you get scatter of this ridiculous number of photons coming off from the phosphor because it's going down to a lower energy band. I added in the blue one, just so you understand, it hits the reflective layer and comes back, right? But they get cast in all directions and there's a spread. And it'll depend on how deep into the material, right? So you don't want a super thick phosphor layer because it'll blur it more. But if it's too thin, you don't get enough. It's a trade-off, right? This is engineering now, right? The thicker the film, the bigger the light response, but also the more blurry the image. That's a trade-off, response versus sharpness. And you can just imagine it goes off equally in all directions, right? And you want to figure out, right, it's going to scatter, so you're going to get this kind of normal distribution as the photons knock through this. Right? So you got a little distribution from the source point coming out, some radius out, say a couple standard deviations, with pretty much the edge of its effect for scattering through that thickness. And that's going to be where the light hits. So it'll cause a slight amount of blurring. Usually that phosphor layer is pretty small, so the effective couple standard deviations is pretty small. But it does blur things. But it increases the image with much less dose. So now, again, you have to kind of make that trade-off choice. I really don't want to give the person more dose to get the contrast otherwise. This will create a tiny blur. I live with it. Does it make sense? So, that explains all these. The spatial frequency you can kind of see coming in here, right? Because of the blur, right? Any blur like that, a Gaussian type spread, is going to be a low pass. So this shows you kind of where it's at, right? So cycles per millimeter, so these are inverse millimeters, right? So you're figuring your minus 3 dB point is usually somewhere around like that 10th or so, So it just gives you an idea of what's going to happen with them. Make sense?
Okay, so is the double-sided phosphor around the film, is that for the X-rays that make it through the first layer?
Because they will.
Okay.
Yeah, they're going to go through that. They're going to go out the back, right? Usually, you put the back of the cartridge. You put something heavier to absorb it, beyond just the material to strengthen it. But essentially, you figure these things are going completely through. They go completely through the film. Right. So what you want to do is you want to get the intensity. If you put double the thickness on one side, it's going to scatter more. Same amount on either side equals scatter, but the thickness hasn't increased. So by doing it both sides, you get twice the amount of light that's coming off it for the same amount of blur. So it's a little more efficient design. So even though they just show one of them here, it's always double, because why wouldn't you? Because these things, like I said, they got way more energy than this. All right. I'm going to go real quick on this one. So this is fluoroscopy. It still happens. It's important for some areas. Same basic idea, though. X-rays come in, layer of phosphor. See those little metal lines? Right? This is similar to like a photomultiplier tube. Essentially, you put a voltage differential across this, and when the photons from the phosphor come in, they're going to hit these, cause a cascade of electrons, which will hit the next one, which causes a cascade of electrons, so it multiplies things. Right? Eventually coming down to where this anode is, it's pulling them in, and then it goes to an image. So this turns X-rays into visible images so it can be viewed real time. That's the real goal of this. All right, so fluoroscopy is real-time X-rays. This is important when doctors are doing surgeries. They have to be able to navigate something. How do they know where they're going? You know, somebody's trying to go do some intravenous surgery. You got to be able to feel that some of it's feel. They planned it in advance, but they've got to see when they get to a branch point. You got to make sure they go down the left side versus the right, or whichever, right? Just pick one at random, right? So when that doctor is having to face this situation, she or he's going to have to make that choice. How do they make the choice? You don't want to do it by guess. That's fluoroscopy. So you watch it and you see what you're doing. Not the greatest for the doctor. They get radiation dose. Not the greatest for the patient, right? So we try to make it so we get as much amplification so we can set the number of X-rays down low. The more multiplication we do within this, the less dose you have to apply. Right? You lower the current because you're getting your multiplier on the other end. So we do that to try to reduce the radiation dose. Like I said, it's usually used for those type of surgeries when they're going in. And they'll only do it when they hit those branching points. When you're going down a longer run, no sense having it on then. Okay, let's just talk about a couple things that happen as an effect. So imagine I've got my detector plane at depth D. Right, D for detector. My object is at depth Z. I've got a point source. Okay? So you can imagine, right, those blue arrows I added in, just to give you the idea, that's the object we're trying to take a look at. So if we were to go from the first object to the second object, obviously it's grown, right, because it's a point source. So it's not going to be parallel and keep the object the same size. Right? We've got triangles. So if you just do similar triangles, right, the small object, the big object, right, you set up that ratio, you'll find out the magnification, right? The big object over the little object is going to be proportional to the big distance over the small distance, the depth of it, right? So the D over the Z. So that's why I just stuck up there, right? It's pretty straightforward, right? It's just similar triangles. So you just have to remember that's the case, right? In addition, there's a second effect that's going to go on here, right? If you think on that detector as they're moving out, if I'm following the upper path here that goes to the top of this object and that hits out there at point XY, which is distance R from the source. All right, so the length of that ray is R. It's kind of hard to understand that in the graphic, but just think the length of the hypotenuse, right, is R. So compare that to the line going right to the center. Its length is going to be exactly D. So there's going to be, they're at really different distances. The one further out from the center is further away. But that means it gets less light. So remember, this is an inverse square law because the surface of a sphere, of whatever radius you have, right, is 4 pi r squared. So it's just the initial intensity at the source, which we have that graph that generates our intensities. So we know what our intensity at the source is. It's just that over this. It's telling me I need to wrap her up.
I always think that's mine.
What's that?
I always think that's mine.
Yeah. The magic of the most common tune that's out there, right? But just remember, right, so this distance, so if you want to think of it, right, the source intensity is the same for both. So if I want to consider how much, I have intensity-wise hitting the unit of space in the center, well, it's just whatever the intensity of the source is divided by 4 pi d squared. But when I get further out at that distance r, right, from the source, it's, the same intensity of the source divided by 4 pi r squared, because it's r from the source. All I have to do, consider the, from the eye at the center, they usually call it I0. That's the very center point of it. So for the I0 divided by, or sorry, I should say the IR, the one at the further out area, divided by I0, how much is that lost, if you want to think of that. Is going to just be the ratio of the R to the D but squared. That make sense? So you imagine that's the inverse square. Well, if you took D over R, because this is D over R squared, that's the intensity drop off. Well, D over R is cosine of that angle theta. Right? Because this is the theta in here. The hypotenuse is R, and the x-axis length is D. Right? So D over R is cosine of theta. So it's the intensity drop off relative to the angle from the source is going to be cosine squared. One other real quick one, just so this makes sense. It's also true that, see those two little circles there in the upper corner, right? In the very center, whatever's coming in hits there straight on. What they're trying to show there is the surface of the sphere is like this, but your actual imaging plane is here, right? So that upper corner, as I'm getting further away from the source, is not actually down on the ground, so it actually casts a shadow, right? So the actual image plane that it hits is, again, gonna cause a dilution, right? Same amount of light over a bigger area, right? So its intensity also is gonna drop. That angle ratio is, again, cosine. So as you go further out, you got cosine squared due to the distance, and due to this oblique angle, you get another cosine. So that means it's going to be proportional to cosine cubed. Right? So the actual intensity does not drop off on the detector plane as a square, it drops off as a cube of the cosine. Okay. So that one's a little bit weird, but hopefully it'll make sense because it's two effects. One is the inverse square, and the other is this kind of oblique angle. The sphere is going like this, but it's a flat detector. So it's the flat detector differential. Right? That gives you the cosine. That's actually everything you need to know to calculate the other stuff. I'll show a couple other pictures at the end, or at the beginning of next time, just because there are a couple other things you just want to understand about. Do we feel good with this? Yeah.
So is this just corrected digitally if we want to make it look reasonable? Or do we just understand that it's going to be faded?
So yeah, it's going to depend on what's like. If you're on film,
Right.
you know, it is what it is, right? You got to deal with it. I can correct it digitally.
Okay.
So that is kind of a nice factor. We can actually take these. Usually what we'll do is we'll take the raw image, and then we'll also provide a post-processed image. But it's usually a good idea, since it's medical data and somebody's life depends on it, to keep the original, and then also produce, you know, when the doctor asks for it. Part of it is if they ask to undo it, you don't want to undo the math, because every time you do and undo in a computer, you don't get a perfect reversal. So if you have the stored original, you can just calculate from the original, and then you don't get this problem of, you know, built up errors within the system. But that's a great question. And absolutely, you know, we would in a digital situation. Cool. Any other questions? Cool deal. Hopefully it's making a little more sense what's going on. There's some kind of weird subtle effects. The picture you can see on the side here is actually from one of, it's not one of the homework problems you're going to do, but it's one of the problems in the text, but it shows this kind of dilution. You can see this is getting closer to the center on the right-hand side. You can see the image intensity dropping off. And a lot of that has to do with this projected unit area spread that's going on. The one's much closer to the center does not have that effect of the curvature. Cool. All right. Well, if that makes sense, I have 2 slides I have to talk about next time, and we'll get into the stuff for CT as well. Good deal. Well, have a lovely day. I will hopefully find my